Welcome back to ece320a. Homework number 2 is due in a week from today. Exam number 1 is due a week from Thursday. And the plan is to go ahead and have a review session after class next Tuesday for exam number 1. But one way that you can prepare for exam number 1, which is on the 14th of February, next Thursday, is to start looking at the review material for exam number 1 on D2L. There should be a unit or a module, and there you should find uncompleted or blank exams that you might test yourself with, and then there are solutions if you want to see I'm stumped, or, oh, he worked it a different way. Oh, I like the way I worked it. We got the same answer. Then it's probably fine. But that's provided for you to try to get you ready for exam number 1. And I have no idea why my hopefully I will work better than the computer. Yes?
Regarding the exam, on previous exams, some of them you allowed a note sheet. Is that going to be kind of...
The question was, will the process for exam 1 be consistent with previous semesters? And the answer is yes. You will get a crib sheet or one sheet of notes, whatever you call it, and you will then create that, and that will be both front and back. It's limited to 8.5 inches by 11 inches. That's your one sheet of notes. So if you see that information on a previous exam, it should be consistent. And we'll talk maybe more about the process for exam 1 in subsequent lectures. Today what I want to talk about is three-phase power, and really making sure that everyone is comfortable with the terminology. And we will define phase voltages and line voltages, and what those mean depend on the connection, whether it's a Y or a delta. So it doesn't always mean a fixed thing what the phase voltage is. The line voltage is always the line voltage, but what the phase voltage is depends on the connection. Likewise, that holds similarly for the currents. You have a phase current and a line current. The line current is always the current in each transmission line, the A-phase transmission line. But the phase current may not be the same as the line current. So we'll try to make that distinction clear in the first part of today's lecture. Then, if we have a balanced three-phase YY circuit, we will extract a single-phase equivalent, which allows us to now tackle three-phase problems, Chapter 11 material, using Chapter 10 techniques, sinusoidal steady state. Except once we find a single phase, if we want to now go and say what's the total, real power, reactive power, complex power, we need to start thinking multiple of 3, since we have the 3 phases, A phase, B phase, and C phase. To be able to convert between, if we're always focused on a YY circuit, well, what if somebody now hands you a Y delta, or a delta Y, or a delta delta? You want to be able to move back and forth between these different interconnected systems to convert them maybe all to a YY so that you can now extract a single phase equivalent. We'll look into how we do voltage transformations and current transformations to make that process more straightforward, to convert from a Y delta to a YY. Then we will actually start looking at formulas that allow us to always just use line current magnitude and line voltage magnitude to actually compute the total three-phase power. be that total real power, total reactive power, or total complex power. We can do that with simple magnitudes. We will also have to know the power factor, or the angle between the current and the voltage, but we can now just have access to this terminal voltage measurement, or line voltage, the current in the line, those magnitudes, and then we'll be able to determine through this expression the total three-phase power. Can't go a quiz or a lecture without a quiz, so we'll have a quiz or an example, and we'll talk then about how we could actually change loads. If we had a delta connected load, how do we convert that into a Y connected load? And we'll do that by looking at impedances when they're unbalanced. And we can immediately create a relationship between the Y configuration and the delta configuration of our loads if we go to the unbalanced transformation and say, oh, suppose all of these impedances are equal. Then we'll see again that there's a factor of 3 relating the Y's and the deltas in their impedances if they're balanced. That's where we're headed, and we may not get to the last pieces of that, but I'll provide that to you if we don't get there. So now let's go through the definitions of phase voltage, line voltage, and then we'll move into the current, line current, and phase current. The first one that we want to talk about is phase voltage, and that's the voltage across a particular phase impedance or a particular phase source. This could be at the generator or it could be at the load side, and we could ask, what is the phase voltage associated with that particular load or source? Let's illustrate that for the loads. On the left we have a Y connected load, and on the right we have a delta connected load, and the appropriate terminals A, B, and C. On the left, with our Y connected load, the phase voltage is the voltage across the particular impedance in that phase. And that phase voltage is actually V sub capital A capital N. That's the phase voltage associated with a Y load. If I say, what's the phase voltage, and you have a load that's Y connected, it's going to be from line to neutral. But now if you have a delta connected load, and I say, what's the phase voltage in a delta connected load, that's actually the line to line voltage, because it's the voltage dropped across that A phase impedance. The phase voltage is always referenced to, or with respect to, the impedance in that phase. And whether it's a Y connected or a delta connected will influence what you're actually meaning when somebody says, what's your phase voltage? It's not the same. Hopefully you can see that that arrow pointing left to a phase voltage is not the same voltage as the arrow pointing right. Those are two different voltages, even though they both will be labeled or called phase voltages. What that phase voltage is depends on how the loads are connected. Is that clear? Yes. The question is, how have I labeled my diagram? Is that true?
Doesn't matter.
Well, the way that I'm trying to do it is, if I now labeled this B would have a positive, and so my VBC would be the B phase impedance. And Z sub C hat is not the same as Z sub C. They may be related depending on if they're balanced or not. But here it's just, now I'm simply saying, if that's my A terminal, I'm going to say that the voltage from A to B is my A phase voltage, with the A terminal being the positively labeled terminal relative to the B terminal. If I wanted the B phase voltage, it would be, instead of just saying it, let me try to write it. It would be this voltage. It would be that voltage. That would be the B phase voltage in the delta connected load. Yes?
So are you saying here that VAN and VAB, are they not considered the same voltage, or
So the question was, you've confused me, Dr. Tharp. You're calling these two things a phase voltage. Are they not the same? No, they're not the same, but they will be called the same. Why? That's just because that is the A phase impedance, and so the phase voltage will be called that voltage for that particular phase. It's the configuration that's different. Here we have the Y configuration or interconnection. Here we have the delta. So if you covered up the left panel or the left side and I said, what's the A phase voltage, or what's the phase voltage in the A phase of the load, you would say, oh, that's VAB. If I then covered up the right panel and said, here's your load, what's the voltage across the A phase? What's its phase voltage there? Then it's VAN. That's the voltage across that A phase impedance. That's how we're defining the phase voltage. And I'm trying to make it clear by it pointing to two different things that it's not the same. It depends on your interconnection structure. Yes?
Reiterate, so for the wide load, it's just across the impedance, and from the delta load is from line to line?
Yes, so the clarification comment was in the delta load, it's from terminal A to terminal B. That's the A phase voltage in a delta connected load. In a Y connected load, it's from the A terminal to the neutral terminal. Because if you look, we're just measuring the voltage across that particular phase's impedance. And it obviously depends then on how your impedances are connected. Yes? Pardon? Oh, what is that middle symbol? Oh, man. Really, that? I just assumed that means is defined to be. That's just a definition. Was that not? I don't know. I just thought that was standard notation, but I don't want that to confuse you. But that's all I'm meaning by that. That just means is defined to be the right-hand side. So that equality is not replacement like in a computer class. It's now a definition. I'm defining the phase voltage to be the voltage across a particular phase impedance or phase source. Is that we starting to feel somewhat comfortable with that definition? Now let me confuse you. Here's, oh, and look. I'm using that symbol again. So there is, I'm defining the line voltage. Now that's the voltage between two line terminals, and that's really transmission line to transmission line voltage. Where now, if you look at the diagram, and I've just, for kicks, I've drawn my Y load a little differently, but it's still in a Y configuration. This just takes up less real estate on the paper or on the screen. But now look at those VABs. They're the same. The line voltage is the same no matter how you interconnect the load. The line voltage is the line voltage. The phase voltage depends on how the loads are connected. Pardon? So this one, now I think the arrow shouldn't be too stressful. Yes.
Do you think we might be able to go a little bit more in depth as to why those two are the same? I'm not exactly seeing it here.
So now, why is this the same? It's meaning that you're measuring that voltage across the same terminals. The question is, go into a little bit more depth. I don't know how much more I can emphasize this, but VAB is just from terminal A to terminal B in both interconnected systems. So when I say the line voltage, I'm really meaning transmission line to transmission line. Whereas in the phase voltage, it depends on how you're interconnected. You're just looking at a particular phase's voltage. Here, I don't have to see, so if you wanted to, I could bury this inside here. I should have had, I should have pulled that out so that, but if all you see are these terminals, it's in a black box, and all you see is an A terminal, a B terminal, and a C terminal, and I say measure the phase or measure the line voltage, you can actually do that. In the other case, if I say measure the phase voltage, you're going to go, well, what's the interconnection structure? Here, you don't need to know it. You could just say, oh, it's VAB in both cases. That's the line voltage.
So for the delta configuration, line voltage and phase voltage are the same?
So the remark was, for a delta connected load, the line voltage and the phase voltage are the same. And I'm just going to turn that on its head when we go to currents. So don't get too hung up on that. Just realize what you're saying. If I ask you for a phase voltage, you say which phase, or maybe I don't tell you, you just say I'm going to get the A phase because that's usually what we do. And then if you need B and C, if it's balanced, you just need to know, is it a positive phase sequence or a negative phase sequence, and you can obtain the other two phases. But here, no, that's a valid observation that the phase voltage and the line voltage are the same for a delta connected load. That's a fact. It will be another fact when we talk about the currents. And you'll then be able to make that point when we get to the currents. Is it clear what I'm trying to differentiate here between the phase voltage and the line voltage? It really only makes a difference on the Y connected loads. The deltas, they're the same. So now let me, use that symbol again, but now let's go into the currents. Here's the phase current, and you can, I think, anticipate what that's going to be defined to be. That's the current through a particular phase of either the load or the source. So we have the two possible interconnections, and to be consistent, I'm looking at it from the load perspective. The Y load phase current is the current going through the particular impedance in that phase. And in this case, that would be I sub A, little a, capital A. That would be the phase current in the A phase. For the delta connected load, the phase current is going through the A phase impedance, but that's not, do you see where I sub AA is in that? I haven't indicated it, but in fact, you would find I sub AA and I sub BB flowing in these transmission lines. I'm intentionally not indicating those on the diagram so that it's clear what I'm calling the phase current. I'm pointing to these two different currents, but they're both called the phase current, and it depends on how those loads are interconnected. And I think you can anticipate where we're going. That's the phase current. Here's the line current. Do you remember what happened with the line voltage? Did it depend on the interconnection structure? No, and the line currents don't either. The line currents are simply the currents flowing through a particular transmission line's phase. So that's the current flowing through a particular transmission line. That's the line current. Meaning, if we look at the Y load interconnection or the delta load interconnection, if I'm talking about the line current, that's always I sub little a capital A. What's not shown here is the phase current in the delta connected load. Okay, now I'm asking for your comment. No. But do you see what's the same now? The line current and the phase current are equal in what interconnected structure? In the Y. Just the opposite of what the voltages were. Because here, the line current in the Y load is exactly the same as the phase current. That's not the case for the delta. The A phase current here is I sub capital A capital B. And that's not I sub AA. I sub AA is made up of an I sub B AB and an I sub CA from KCL. You know KCL always holds true. When in doubt, pull out KCL or KVL, right? That should always be true. But in this class, what do you have to remember? You're dealing with vectors or you're dealing with phasors. It's not just magnitudes. It's not just numbers. It's magnitude and an angle. You have to add them vectorially. That's the line current. In this case, the line current for the Y load is the same as the phase current in the Y load. That's not true for delta loads. Yes?
So for when you say like the phase voltage and the line voltage are the same for the delta load, like they're numerically the same thing? Like if we were to make an equation with it, we could just replace, for example, the delta load just.
So when I'm saying that the delta load for the delta load configuration, the phase voltage is the same as the line voltage. I'm just saying that you're measuring the same quantity. You're measuring between terminal A and terminal B in both. That's what I'm meaning by they're the same. You're just looking at the voltage between terminal A and terminal B. That's all I'm really saying when I say they're the same. What we will want to do, though, if maybe somebody gives you a phase voltage in a Y configuration, you may actually want to compute the line voltage or vice versa. And we'll find those relationships in just a minute. We'll see the connection between these different voltages in the Y configuration and the different currents in the delta configuration. How do we relate I sub AB with I sub AA? That's what we want, and we'll talk about that when we are dealing with balanced systems. Can we convert between those? If somebody now measures a voltage across the terminals, can you now give them the phase voltage for a Y-connected load if everything is balanced? That's involving definitions. You need to be comfortable with those definitions. Now let's talk about extracting, really simplifying this three-phase system to a single-phase equivalent circuit so that you can now find these voltages and currents in one phase. And once you have them, if everything is balanced, you know how to find the other currents and voltages for the other phases. They're the same magnitudes, just differing by 120 degrees, depending on whether it's a positive phase sequence or a negative phase sequence, how the ABCs and the ACBs are related. From the last lecture, from the previous lecture, we said what constitutes a balanced three-phase YY circuit. Our generator impedances are the same. In the A phase, B phase, and C phase, we're assuming that the impedances in that generator are the same. We're assuming the transmission line impedances in all three phases are the same. We're assuming that the impedances in all three phases are the same. Meaning I could just say Z sub little l, or Z sub little g, or Z sub phi. And if it's balanced, you know that all the phases have that same impedance. And the sources form a balanced set. What does that really mean, or what is that saying? When I say the sources, we have three sources, an A phase, a B phase, and a C phase. How do three voltage sources form a balanced set? What do we know about their magnitudes? They're equal. What about their phases? They're off by 120, and they'll be 120 off either in the ABC or the ACB, either in the positive or negative. And you'll just have to be told if somebody needs that much information. Is this a positive phase sequence or a negative phase sequence? Sometimes you don't even have to know the phase sequence to solve the problem. Many times. And if you're not told and you think you need it, I would just assume a particular phase sequence and work from there. You've already beat me to this, so I'm sure you've already sketched this when I said we were dealing with a three-phase YY circuit. If not, you can go home and make copies and then cut and paste. I don't know how you do it now in today's. Maybe you have a soft copy and you can just circle it, cut and paste it in. That's how I cheated. So this is now our system. This is our three-phase system, and we're assuming it's balanced. The G's are all equal, the Z sub little l's are equal, and the load impedances are equal. That's our balanced three-phase YY interconnected system. If we now perform KCL at the reference node, what do we know about I sub 0? The current in the neutral conductor. Or if these are now balanced currents, a set of balanced currents, what can you see? Do you see a triangle? So you have I sub A, and if that's the reference, if you've drawn the line in the sand, that's going at 0 degrees. And if this is a positive phase sequence, what's I sub B? That's at minus 120. I'm going to run out of space, but I'm walking a triangle. Could you tell? So I'm going positive, I sub AA, then I go minus 120, I sub BB, and then I go back. Do you see the triangle now? I see a triangle. That's what you should see here on the right-hand side. And if it's a closed triangle, what's really happening? Isn't that equal to 0? That balanced set of currents is equal to 0. That's an ugly 0. Somebody's going to comment on it, so let me try to make it a little neater. Okay. That's not much better, but we see that I sub 0 is 0. Now what does that tell us? If the current in that neutral conductor is 0, what does that allow us to do? We could either remove it or we could replace it with a short circuit. There's no voltage drop, so the voltage here at little n is the same as capital N. So we could just connect that with a short-circuited wire. And if that's the case, now we can actually just extract that very top mesh into a single-phase equivalent. Z sub 0 is immaterial. Since there's no voltage dropped across it, we can just replace it with a pure line, and now we can make the following observation. We can now extract a single-phase equivalent circuit, and it's going to look as follows. We have our generator voltage, which is a phasor. We have our generator impedance, Z sub G, and I'm just doing this for the A phase, but this could be in general, it could just be Z sub G. And here would be our terminal that the outside world would see or connect to. A prime may not be accessible to us. Here is little n. We have our transmission line impedance. And then we have our load impedance. And that's now our single-phase equivalent from a balanced three-phase system, where we can now say, oh, here is our line current or our phase current in the A phase, I sub AA. Here in the neutral conductor, we are not putting any impedance. There's no impedance because we've shorted that out. Questions on that circuit? That should just be what you see in one of the phases of that three-phase equivalent. Question?
Can we go over why that I of 0 equals 0 one more time?
So somebody didn't like my triangle. Why is I sub 0 equal to 0? So now we're saying that I sub AA, I sub BB, and I sub CC form a balanced set of currents. That means that they look like this. And those are all supposed to be the right size. Here's I sub AA, I sub BB. For a positive phase sequence, I sub CC. And if you add those up, head to toe, you'll have this, that, and that. So here is I sub AA. Here's I sub BB as a phasor, and here is I sub CC. And I hope that you can see that they are starting and ending at the same point. So we get 0 when we add those up vectorially or as phasors. That's why the sum of A sub AA plus I sub BB plus I sub CC, that's why we can conclude that that's equal to 0. And once we've concluded that, that was equal to the current in the neutral conductor, I sub 0. That allows us now to either short it out or remove it. It helps us in our analysis to short it out and come up with this single phase equivalent. Yes?
The voltage generated by the source does
So the voltage source now, everything is taking care of the balanced configuration. We've assumed that these generator voltages are a balanced set of voltages. And if all of these impedances are equal, then we have that condition. All of the currents will be forming a balanced set of currents. And that gives us our triangle. That's what I was meaning in a sort of joking way, but we walked that triangle, and that brought us back to 0. And we're doing that because these are phasors, or we can create that because they are phasors. Now, there's a couple of things we need to keep straight relative to this single-phase equivalent and how we can generalize that to the three-phase circuit itself. So let me make 2 notes relative to that. The first note says that this current, I sub AA, in the single-phase equivalent that I've just labeled is exactly the same as the I sub AA, or the line current, in the balanced three-phase circuit. And that's a good thing. That means you can now do your analysis in this single-phase circuit and actually come up with the answer that you would need in your three-phase big circuit. Those currents are exactly the same. But what you don't want to do is assume that, well, let me just write it down and hopefully it will be clear. I sub AA, which is the current in the neutral conductor. Do you see that I sub AA is just a series current, and it's going to be flowing in the neutral conductor here in the single-phase equivalent? You can't assume that that current in this neutral conductor is the same as the current in your neutral conductor of the three-phase. The neutral conductor in the three-phase has both the A phase, the B phase, and the C phase combined to give us 0. That's the second note that I'm trying to write. I sub AA, the current in the neutral conductor, in the single-phase equivalent circuit is not equal to the current in the neutral conductor of the balanced three-phase circuit. Because this one is I sub 0. And I sub 0 is not the same as I sub AA. That's all I'm saying. So don't overgeneralize too much from the single-phase equivalent. I sub 0 is equal to I sub AA plus I sub BB plus I sub CC, and this is the actual neutral conductor current. And that is equal to 0 for our balanced circuit. So if you're wanting to solve these three-phase circuits, if you now have a YY configuration, you can immediately, if it's balanced, you can pull it out, the A phase or the B. Usually, let's just agree to do the A phase and solve it, and now we can go and get anything we want for the other phases based on the solutions here. What we may want to do, though, is go back and forth or find information. Maybe somebody says, well, you analyze that single phase equivalent, and maybe you now have the phase voltage at the load. What's the line voltage between A and B? That's not in my single phase equivalent. How do I find that? Well, let's figure that out, okay, based on knowing the phase voltage at the load for this particular circuit. Let's now look at doing transformations between those voltages. And this really only makes sense if we have a Y configuration. Yes?
I have a question about the neutral conductor.
The neutral conductor.
If,
He's driving a train.
if,
It's not very good.
Sorry.
if all the currents add up to zero, does that mean like if somebody touches it, they won't get electrocuted? Or like if you put like
Okay, who wants to put their life on the line? I was looking for a graphic. I have a graphic. Maybe I should bring it. But the question, I think, was how brave am I, or how much am I willing to risk some of this? I wouldn't put my life on the line for that because it doesn't take much current to kill us. But you're saying, oh, is there zero current flowing in that neutral? If now somebody trips a load offline, now your circuit is imbalanced. Yes, there's going to be current flowing in that neutral conductor. So if they say, oh, look at him, let's show him something, and they take something out or change one of those impedances, you're a crispy critter. So I wouldn't be playing around. We can do it on paper, and we can do it with analysis, and that's how we're able to solve these problems, is by assuming that everything is balanced. But I wouldn't want to put my life on the line or your life on the line by saying, well, he said there's zero current. Let me just see. I'm going to touch both terminals. Not a good idea, okay? Because something could get messed up. Somebody might have knocked an impedance out of whack, and now you're really flirting with disaster. Yes?
This is ideal, right? So in real life, there could be small, minute variances in the impedances of the lines themselves.
Yes, this is the ideal scenario, and that's where we're living right now. We're in an ideal environment. I bet you didn't realize that. This is an ideal environment that we're working in, that we're studying in, and you'll take a test in an ideal environment. It will now be that all these ZGs, all the ZLs and the ZAs, or the ZB, all those are equal. But yes, that's the assumption that we are living on, that there's now no impedance in that neutral conductor, and in the three-phase system, there's no current going through it. And if there's no current, then there's no voltage drop across that. Now, let's figure out how we convert between a phase voltage and a line voltage in a Y-connected load. We're now relating V sub AN. Let's say that that's now, we'll just make this a magnitude of V sub phi, and we'll call this our reference phasor, so we'll just tag it to be at 0 degrees phase. This is our phase voltage. And we're really relating this to the line voltage, which is V sub AB. Is it possible to find a fixed relationship? How does the magnitude change? How does the phase change between V sub AB and V sub AN in a balanced three-phase configuration? Because we will be able to find in our single-phase equivalent V sub AN. That's just this voltage drop. But do you see V sub AB anywhere in this single-phase equivalent? But now if you're measuring or testing and you tell an engineer to go out and measure the line voltage, he's going to measure VAB. Well, now you can check whether his measurement is consistent with your analysis after we've figured out how to relate V sub AN to V sub AB. Let's see what that relationship is. We're going to derive it.
I was just gonna, I don't know if I'm getting it at, but aren't you just gonna find VAN by finding, like, doing equivalent impedance?
So now how would you find V sub AN in this single phase equivalent? I'm not going to tell Dr. Marcelin. Ohm's law, right? So in this case, if somebody gave you V sub A prime N, that's a phasor. You now know all of these impedances. You can sum those up, divide those into V sub A prime N, and that gives you I sub AA. Or you could do a voltage divider, but once you have I sub AA, you can multiply it by Z sub A, and now you have V sub AN. Now you've got V sub AN, you can carry it, right? But you're carrying this around, V sub AN, and somebody doesn't want it. They only want to buy V sub AB. They go, I could just measure V sub AB. I can't go in and measure that I can't access that. It's behind something. So maybe all they can measure is V sub AB. And they say, is that right? And you go, I'll let you know if it's right or not based on what I have in V sub AN. That's what we're trying to determine now, the relationship between these two voltages, the phase voltage and the line voltage. Is it clear what we have? We may have the phase voltage. We want to find the line voltage. Or on the exam, I might say, here's your line voltage. What's the phase voltage? And you can do this in reverse. It won't be a rut-row. It'll just be a calculation. Because we're doing this in an ideal environment, you're all going to get A's, right? Sure, you're going to earn an A. You're not all going to get or be given anything, right? Have to be careful what I say. So we're relating V sub A, the phase voltage to the line voltage, which means we have Z sub A, Z sub B, and Z sub C, and that was a capital C. There's V sub AB. And what we might have, though, is V sub AN. And that's from here up to there. Here's A, B, and C. If we're working with a balanced set or a balanced system, if you give me V sub AN, you know V sub BN, because it's in a positive phase or a negative phase sequence. So we can now find or compute V sub BN from V sub AN, or we know that relationship. Meaning, if I now say, oh, let's just do this analysis right now for an ABC sequence. And I'm going to assume, as I did above, that V sub AN is now V sub phi at an angle of 0. Can you now tell me what V sub Bn is? There's partial credit. Out of 10 points, that's 1 point out of the 10. So now an ABC says if you're standing there and watching, you see the A phase, then the B phase, and then the C phase. So that means B is at minus 120. And that's also RMS. And the C phase, we won't use it, but you know what it is. We now know that that's given. That's what we're saying we have. Now what we want to do is, knowing this information, can we now compute or relate V sub AN to V sub AB? And now we just fall back on what we know, right? KCL or KVL. We're dealing with voltages. Let's just do a KVL equation. We have a mesh looking at us, and it's going to involve V sub AB, V sub AN, and V sub BN. Let's write that KVL equation. KVL now, in this Y configuration of a load, says that minus V sub AB, all I'm doing is going around here. So I have minus V sub AB plus V sub AN, then what? Minus V sub Bn. And I'm back to where I started, and that's equal to 0. That's simply KVL at the Y. Let's now solve that for VAB. Or adding VAB to both sides, then VAB is simply VAN minus VBN. But what did we say? We said we already had a particular notation for those two voltages on the right-hand side. V sub AN was V sub phi at 0. V sub Bn, we're subtracting, is V sub phi, same magnitude, and its angle was minus 120. So that now V sub AB, the magnitude's the same. We can just combine these phasors. We have a 0 degree phasor, and we have that, or we're subtracting from that a minus 120 degree phasor. These have a magnitude of 1 at an angle of 0, minus 1 at minus 120. You can think of these or look at these however you want, but this is now 1 at 0 degrees, which is e to the j 0 degrees if you wanted to think of it that way. And this one is just e to the minus j 120 degrees. And you can now use Euler to find those. You expand this with Euler and you have cosine of minus 120 degrees plus j sine of minus 120 degrees. That's what the angle of minus 120 looks like. And what do those produce in terms of numerical values? You could simply pull out your calculator and compute those, or you could start drawing triangles and figuring this out. But now I know that V sub phi, that's the angle. 1 at 0 degrees, that's just the number 1. That just has the real part. So there's a 1, dropping that down. Then I have minus. I'm not going to worry about that. Let me just say minus. And now I'm going to take and expand that angle of minus 120, which I've just done. That's now in rectangular form, cosine of minus 120 degrees plus j sine of minus 120 degrees. Need to make sure I have enough parentheses here. Do you see what this is? Here's minus 120 degrees, roughly. And this length is 1. That's my hypotenuse. And so the cosine of this angle is that distance. What is that distance? This is really just a, if we wanted to think about it, this is a 30 degree, 60 degree right triangle. And it has a hypotenuse of 1. That means that this side opposite the 30 is how long? It's half of this hypotenuse. So we're now minus 1/2 is what the cosine of minus 120 is. I forgot my calculator. Well, you didn't even need it. You can think your way through that analysis. So if this is now the cosine of minus 120, it's minus 1/2. What's the sine of minus 120? What's this length? Just pull out Pythagoras, right? A squared plus b squared is c squared, and c squared is 1. This is 1/2. That's actually the square root of 3 over 2. Just doing Pythagorean theorem. So we now have all of this information available to us. We now know that v sub phi is now 1 minus a minus 1/2. And we're actually down for the sign. It's minus j square root of 3 over 2. Everybody comfortable with that trigonometry or that geometry? You could just plug it into your calculator, or you could start drawing triangles. But that's how we know this is now v sub ab. But we can clean this up. That's just a complex number that's weighting a number. And that complex number has a magnitude and an angle. And that's going to now adjust the magnitude of our phase voltage v sub an. And that will be our relationship between our phase voltage and our line voltage. What does this become? Now we have v sub phi. We have 1 minus a minus 1/2. This is really tough, isn't it? So we have 1 plus a half, 3.5 for our real component. And we have a minus j square root of 3 over 2, or we have a plus j square root of 3 over 2. There's a complex number in rectangular form. Let's convert it to a magnitude at an angle. So we take the real part and square it. We take the imaginary part and square it. And our angle is now just the angle that has a tangent of the square root of 3 over 2 over 3 over 2. And what is all of this? This is now 3/4 plus, can't square 3 today. 3 squared is 9. And the square root of 3 over 2 squared is 3/4. That's now 12 over 4, or 3. So the magnitude is a square root of 3. what's this guy? Well, this is now the inverse tangent of the square root of 3 over 3. Or the inverse tangent of 1 over the square root of 3, which is really, back to our 30-60 triangle, that's 30 degrees. So that this v sub phi is now going to be adjusted by a magnitude stretch of a square root of 3 and a phase change of 30 degrees. And we can make this look more like what we started with by simply writing v sub phi as v sub phi at 0 degrees, and then that's scaled by a square root of 3 at 30 degrees, where this was our phase voltage that we started with, and this is now the relationship between our line voltage V sub AB and our phase voltage V sub AN for the A phase. V sub AB will be a square root of 3 bigger in value and magnitude, and it will be advanced by 30 degrees from whatever our phase voltage was before, which we assumed was at 0 degrees. And if you drew this, if this is now V sub AN, then if you could draw this accurately, here would be V sub AB as a phasor. It's 30 degrees, and it's the square root of 3 times V sub phi. This is just V sub phi at 0 degrees. And do you see how to make this even more interesting? By filling in the other phases. We're dealing with a three-phase balanced system, so you can immediately, if this is V sub AN, you can immediately draw V sub BN and V sub CN. They're 120 degrees away from V sub AN. So that now V sub BN is right here, and V sub CN is right here. And you can now draw in the other line voltages because they differ either 120 degrees away from VAB or square root of 3 and 30 degrees from these phase voltages. Doing that, we could then write or sketch. There's the B phase phasor, V sub BC. That's straight down because that's now at minus 90 if VAB is plus 30 and they're 120 degrees apart. And V sub CA is 120 degrees sort of counterclockwise from V sub AB, so it's 30 degrees beyond V sub CN. It's at now 150 degrees, but this is now V sub CA. And if you don't like my diagram, you don't have to live with it. You can now go into the book and find that in figure 11.9 part A. And this is for a specific sequence. We assumed a positive phase sequence. Yes?
I'm assuming that's why it's called positive phase, because the phase voltage leads to the
So you could say, well, the way I'm going to remember this is now this is a positive phase. Well, now it's 30 degrees bigger, the line voltage is, than the phase voltage. That's just for voltages. The negative phase sequence will be the same scaling. It'll still be a square root of 3 bigger. So if you just need to know size, you've got it with this square root of 3. But now the ABC will be 30 degrees behind the phase voltage. But that's figure B, and I'm not going to bore you by sketching it.
That's not why it's called positive.
That's not really why it's called the positive phase sequence. It's just ABC. ABC seems like it's positive in terms of how we think of it, ABC. Negative is ACB. That's how I would view it. I wouldn't try to get too hung up on why is it called positive, but you do need to know that for a positive phase sequence, this is the relationship between your phase voltage and your line voltage. So if somebody gave you the phase voltage, you could immediately find the line voltage by this square root of 3 30-degree relationship. Or if somebody gave you the line voltage, you could back out and say, oh, my phase voltage must be this, by just doing the opposite. If you now need to find V sub A n, do you see that you could divide both sides by the square root of 3 at 30 degrees and find V sub A n, just solving for V sub A n.
So would V sub en and then V sub ca be also like 30 degrees off?
So what do you know? The question was, how are V sub Bn and V sub Cn? This drawing may not do justice to what's happening, but these blue lines have to be advanced 30 degrees from the black lines, and they have to be expanded by a factor of the square root of 3. And we know that the B and the C phase and the phase voltages are balanced, so they're 120 degrees away from each other. Have the same magnitude, they're just 120 degrees away from each other. That's our voltage transformations. Now what we want to understand are the connections with our line currents and our phase currents. How are the line currents and phase currents related in a, it would be trivial to ask in a Y configuration because they're the same. So now we need to ask, how are they related in a delta connected load? Meaning, if I now have Z delta here, and I'm just going to call it Z delta here, and Z delta here, and this is, let's say, my A terminal, here's my B terminal, here's my C terminal. Here's my line current in the A phase, I sub AA. Where's my phase current in the A phase of the load? It's this current, which is I sub AB, passing through the A phase load impedance. That's the phase current for this delta connected load. But I sub AA is made up of more than just I sub AB. It also has this current making it up because of KCL, and this current is I sub CA. Where now, if we just wrote KCL at the A terminal, what would the expression be? Sum of the currents in equal to sum of the currents out is one way of thinking it. Just the algebraic sum of those currents have to equal 0. Or you could say, oh, let me say that I sub AA is going in to terminal A, as is I sub CA. Those two are going in to terminal A, and going out is I sub AB. And now I can relate the line current, I sub AA, to the phase current just by writing one KCL equation. I now can say that I sub AA is equal to I sub AB minus I sub CA, where this is the A phase line current, and this is the A phase phase current. Because that's the current in the A phase impedance of that delta connected load. If I now assume a positive phase sequence or an ABC sequence, and I assume that I know, or I'm just going to have as given the phase current in terms of a magnitude and an angle, and I'm going to use that as my reference. Now, what is I sub BC? That's the B phase current, and if they're forming a balanced set of currents, they have the same magnitude, just differ in angle by 120, and this is the B phase, so it's at minus 120 degrees, and I sub CA is 120 degrees. Now we can do what we did before. We can plug in, we can say, oh, I sub AA is just I sub AB, which was I phi at an angle of 0 degrees, minus I sub CA, which is now I sub phi at an angle of plus 120 degrees. And there's just a little bit of a difference. Before we had an angle of minus 120 being subtracted. You go through the math or the algebra like we did before, and you're going to see that now we have a square root of 3 at minus 30 degrees connecting this phase current of I sub AB to the line current I sub AA. And does that make sense? Now the line current is a bigger current than the phase current in a delta connected load. And one way to maybe sort of justify that or give you some intuition into that is just look at what's happening at terminal A via KCL. It takes two phase currents to combine to make one line current, is one way of thinking. So the line current must be a little bigger, and it is. It's a square root of 3 bigger. Its phase, though, is not the same in terms of its direction. It's now minus 30 degrees relative to the phase current in the A phase. And this was for an ABC sequence. And you could sketch this if you wanted to, the different phasors. I'm assuming you'll go home and do that. It's probably a figure in the book. I didn't write that down. But now what do we have coming up? Now we have an ability, by just analyzing a single phase circuit, to find different quantities. We could find the line voltage from just knowing the phase voltage. Or if somebody gives you a line current and they say, oh, this is really a delta connected load, you can now find the phase current flowing in that particular load's impedance. What we want to be able to do next is say, wait a minute, I just want to be able to calculate total power based on measured quantities. And what can we measure probably in the field? The line voltage from transmission line to transmission line and the line current, the current in the line. Can we now find power equations just using those two and maybe the angle of our impedance. That's where we will pick up with next time.